Okay, in this video we're going to consider another combination with repeats type problem, and it's a little bit of a different style, if you will, than the previous problem that we worked. And here's what we have. 30 marbles are going to be distributed to 5 children. And we're asking ourselves, how many ways can this be done, keeping in mind that perhaps maybe one child will receive all 30 marbles. So in some of the distributions, it's possible that some of the children won't receive any marbles, and obviously some children can receive multiple marbles. And of course, this is what makes it a combination with repeats, because multiple marbles can be distributed to different children. So the formula that we developed in the previous videos was n plus k. Think of it in the classical sense now, without invoking generating functions. It was n plus k minus 1 factorial divided by k factorial times n minus 1 factorial. Now, in some of these problems, it can be not readily apparent what is n and what is k. Now, in the past videos, we said n, that is supposed to represent the number of objects to choose from. And k is supposed to represent the number of selections. So in this problem, what is n and what is k? Well, we have 30 marbles that we're distributing, so you might be thinking, all right, then we've got 30 objects to choose from, 30 marbles going to 5 children. But actually, in this problem, the number of children, that is n, and the number of marbles, that is k. And to understand why, let's go back and just briefly reconsider how this formula was derived. Remember, we considered the situation where we had 6 crates and each one was filled up with pieces of candy. And we could imagine that maybe each crate has a different flavor of candy. So there are 6 different crates, and we could select a total of 10 pieces of candy from these 6 crates. So in this problem, n is the 6 crates, the 6 different crates, we should say. And the number of selections we were making was 10, so that was the k part of the problem. Now, to solve the problem, remember how we set it up. I said, well, let's then suppose that we have 10 pieces of candy, like this, and even though the candy now might be of different flavors, we were considering them as all identical X's here. And the reason for that is when we're making our selection, there's no rules that say, well, we have to have so many cinnamon ones, or we have to have so many vanilla ones, or we have to have so many apple-flavored ones. So in that regard, when we're making our selection of 10 pieces of candy, there's no rules about it, so they're all, in that since they're all treated identically. So that's why we represent this as 10 identical x's here. And then we said, suppose that we distribute these into 6 different boxes. And we asked ourselves, how many different ways can we do that? And when we thought of this problem in these terms, that's when we got the formula. Lo and behold, the formula popped out that we were able to derive. Okay, so now here then we have, when we were setting this problem up, we have k number, in this case 10, but k number of identical objects, and they were going to be distributed to 6 or n number of different boxes. So here then we have, we're doing our distribution, we have 6 different objects to choose from. And that's what the n is. N number of different objects to choose from for our k number of identical objects. And that's the way our current problem is set up, just like that. We have 30 marbles, and they can be different marbles too, but there's no rule saying, well, if a marble is a certain color, you can only give a certain number away, or if a marble maybe has an imperfection, it has to go to a certain child. There's no rules like that at all. So we can treat the 30 marbles as if they're identical. So here we have 30 of these identical x's, and we have 5 children to distribute them to. Or, if we want, we can think of this in terms of 5 different boxes. We want to know how many different ways then can we distribute these 30 x's into these 5 different boxes. So when we're doing our distribution, we have 5 different children or 5 different boxes to choose from. So this number of children or number of boxes is considered n. That's the number that we have to choose from when we're distributing these k number of identical x's. So in this problem then, n is the number of children, and of course n equals 5. The k number of identical objects is 30. So that's the k variable. So now this problem is simple enough that we can just use the classical approach. Divided by k factorial times n minus 1 factorial. Okay, and let's see, this is 5 minus 1 is 4 plus 30, so that is 34 factorial divided by k factorial, that's 30 factorial. And this here is n minus 1 is 4 factorial. So let's see what that gives us. We have 34 times 33 times 32 times 31 times 30 factorial divided by 30 factorial times 4 factorial. 4 times 3 times 2 times 1. 4 times 2 is 8. That goes into there 4 times. And this goes into here 11 times. These cancel. 44, so we have 34 times 44 times 31. And I think if we put that through on the calculator here, it's 46,376. So that's the number of ways then that the 30 marbles, or the number of possible ways that the 30 marbles can be distributed to the 5 children. Okay, well now let's consider this same problem as to how we would approach it using generating functions. So here we have 5 children to distribute 30 marbles to. Now, how do we set up the generating function to begin with? Here we realize, well, for one child, he might not receive any marbles. So that's 1, or x to the 0. Or they might receive 1 marble. Or they might receive 2 marbles. Or 3 marbles. And so forth. Now, here, we just write this as going on out to infinity. Now, you might think, wait a minute, even if one child receives all 30 marbles, then that should stop here at x to the 30, because you can't receive any more than 30 marbles, yet you're writing this, I'm writing it as an infinite series, as if it continues on forever. And it does continue on forever. Where the 30 comes into play, as we'll see in a second here, is we consider x to the 30 power once you multiply all these generating functions together. We'll get to that in just a second. If, however, we said, well, no, each child cannot receive more than 3 marbles. That's the limit they can have. Then, in that case, we would stop at x to the 3. So, here, if there's no restriction stating that a particular child or any child can receive only so many marbles, if there's no restriction like that, then we write this as an infinite series. And in the next video, we'll demonstrate when you do have that kind of restriction. But for right now, we're taking a simpler kind of a problem. With these generating functions, they're very powerful, but you can't simply, even for just the basics, demonstrate all their properties in one video. So we just have to do it in a series of videos, and hopefully this will be useful to you. But okay, so for each child, we consider they might receive no marbles, which would be x to the 0 or 1, or they might receive 1 marble, or 2 marbles, or 3 marbles. No restrictions are stated, so this just continues on out to infinity. And remember, this is equal to this. Now, this is true for each child. And we have 5 children. So here then, to consider all 5 children together, we multiply all 5 of these together, which is going to give us 1 to the 5th over 1 minus x to the 5th. Or that will equal 1 minus x to the minus 5. Now, when we expand this out, this is then when we want to consider the coefficient of x to the 30 power. And that coefficient then will tell us the number of ways that we can distribute 30 marbles amongst the 5 children. So, remember what our formula is. 1 minus x to the minus n. In our previous videos when we dealt with binomial expansions and negative coefficients, we determined it to be this. And so forth. This was our pattern, where this number this part stays the same. The number that we add to n is 1 less than that exponent. So it continues on like this as an infinite series, and then for x to the 30 power, that would be n plus 29 divided by n minus 1, and then we continue on with all the other terms. But we're interested in the coefficient of x to the 30 power. Now here we're saying x to the minus n, so n equals 5. Because it's to the minus 5, we already have the minus sign there, so n equals 5. So this is 34 over 4. And this is equal to 34 factorial divided by 30 factorial times 4 factorial. That binomial coefficient is this, which is the exact expression that we had just worked out previously, or in just a couple of minutes ago. So you can see that the same problem can also be solved using generating functions. Now what we're going to do in the next video is consider, again, this kind of a situation, but now we're going to have restrictions on it so that we can't just use the classical approach. The only way we can solve it is by using generating functions. So come back and join us for that video, and we'll continue along and solve some more problems.